All right, so hi everybody, welcome back. Today we're going to be starting a new chapter. That's chapter 34 of the textbook. And what's covered here is the wave nature of light and interference. So in this chapter, we're going to talk about ways that light acts like a wave. So we can apply everything we know about waves that we learned back in chapter 15 to light. And in particular, we're going to focus on an effect that light undergoes called interference. So the idea that two light waves can interfere with one another, that's what we'll talk about here. So the first thing to discuss here is something called the wave-particle duality of light. So this is the idea that if we go into the laboratory and we do different experiments on light, we test out how it behaves under different circumstances, we'll find that the outcome of our experiments in some situations is best understood if we think of light as some type of wave. On the other hand, there are other experiments that we do that really only make sense if we think of light as a type of particle. So rather than being a wave that's traveling in a particular direction, it's a stream of particles that's traveling in a particular direction. So that's very strange. This implies that light really doesn't fall neatly into either one of these categories. Okay, it's a little bit more subtle and complicated than that. So what I'm going to do in this section is tell you some of the experiments that take us to the idea of wave-particle duality, and then also some of the history that led us to this idea in the first place. So throughout the history of physics, people have wondered about the fundamental nature of light. The question is, what is light actually made out of? And if we go to the early days of physics, around the time of Isaac Newton, there were basically two competing ideas, which are the wave and the particle models of light that I told you about earlier. Now, Isaac Newton himself was a firm believer in the particle model of light. He thought that when you see a light ray go by, what you're seeing is a stream of tiny little particles traveling along that light ray. At the same time, you had people like Christian Huygens, who was a big rival of Isaac Newton's, who argued that light must be some type of wave. And Newton and Huygens argued back and forth for a long time about which of these models was correct. Now, if we fast forward in history about 100 years or so to the early 1800s, this guy Thomas Young comes along and performs an experiment which we now call the Double-Slit Experiment. And I'll tell you a lot about this experiment throughout the chapter. We'll keep coming back to it. But basically, this experiment convinced most people at the time that light must be some type of wave. And then later on in the 1800s, Maxwell developed his equations of electricity and magnetism, which also really gave a lot of support to the wave model of light. So by the end of the 1800s, most physicists were convinced that light is some type of wave, and it wasn't really questioned. But then Albert Einstein comes along in the early 1900s, and he showed that there are some properties of light, some things that light does, that can only be explained with the particle model of light. So we're left in this weird situation where some experiments really support the wave model of light, and other experiments really support the particle model of light, and we're in the current state of things where we have what's called the wave-particle duality. So what we'll do next is take a look at some properties of light, some things that we know light does because we study it experimentally, and we'll see if those properties fit with the particle model of light or the wave model of light. That way, we'll kind of see what sort of evidence there is for each of those two models. And we'll start with the inverse square law. So back in chapter 15, we learned about the inverse square law. We saw that if you have an isotropic source of waves, it will follow an inverse square law, where the intensity of the wave is proportional to 1 over distance squared, or distance to the minus 2 power. So of course, an isotropic source of waves follows the inverse square law. It's also true that if you have an isotropic source of particles, so that would be something that emits particles outwards from a source in equal numbers in all directions, that would be an isotropic source of particles, then the intensity is also going to follow an inverse square law. So the point of this is to say that the inverse square law is consistent with both the wave and the particle models of light. So both of these models are consistent with the inverse square law. So let's take a closer look at what happens when we have an isotropic source of particles. What I want to convince you of here is that the intensity is going to follow an inverse square law. So we'll start by supposing that there are n particles emitted by the source per unit time. So let's call that time t. And let's also suppose that each particle has a certain energy, and we'll call that energy E naught. Okay? So we have n particles being emitted every time t, and each particle has energy E naught. Okay, so the next thing we'll do is label this little surface here. This surface is a spherical surface with radius r. So here's the radius of the surface r. Okay, so what is the intensity then? Remember, the definition of intensity is energy flowing through the surface per unit of time per unit area. So let's work out what that would be. So we have the total energy flowing through the surface per unit time, which is t, per unit area, which is a. Now, the total energy flowing through the surface would just be the number of particles that are flowing through the surface, which is n, times the energy that each particle has, which is E naught. So we have n times E naught on top. On the bottom, we have the time t, and then the area of our surface, which is 4 pi times r squared. So the point here is n, E naught, and t, and then the 4 pi factor, these are just a bunch of constants. So the intensity is proportional to 1 over r squared. This follows the inverse square law. So whether we think of light as a particle or we think of it as a wave, it will still follow the inverse square law. So the fact that it follows the inverse square law doesn't really tell us either way whether we should think about light as a particle or a wave. It's pretty much indifferent to that question. And so that takes us to the double-slit experiment. This was an experiment that was carried out for the first time in 1801 by Thomas Young. And his goal was to test his idea that light is a type of wave. So Thomas Young was a believer in the wave model of light, and he wanted to prove that to other people by carrying out this experiment. So here's the experimental setup. So first, we have rays of sunlight coming in, and those rays of sunlight go through a very narrow slit in the first screen shown here. So first, we have a screen with a single narrow slit that the rays of sunlight will go through. Then next, we have a screen with 2 narrow slits. So this is what we call our double-slit screen. And the rays of sunlight, after going through the single slit, will go through the double slits. And then after that, the light will be projected onto a viewing screen. Okay, so this is where we just take a look at what the light looks like when it comes out of the double slits. Now, the reason we want to know what happens at the viewing screen is that the wave model and the particle models of light make very different predictions about what should appear on the viewing screen. And so let's get into that. If we think that light is just a stream of particles and that's the end of the story, This is what we'd expect to happen in the double-slit experiment. You'd expect that some of the particles are going to go through the slit on the right, which produces on the viewing screen a single band where those particles are just striking the screen. But some of the particles are going through the slit on the left, which produces a separate band where those particles are hitting the viewing screen. So you just see two bright lines on the viewing screen if light is just a stream of particles. That's what you'd expect to see. On the other hand, if we think of light as a wave, the prediction is much different. This is what we'd expect to see on the viewing screen in that case. Not just two bright bands, but a whole series of bright and dark bands on the viewing screen. And the reason for that is effectively we have a different wave coming out of each slit. So there's a wave coming out of this slit and a wave coming out of this slit, and those waves can interfere with each other. Sometimes you'll get constructive interference, other times you'll get destructive interference. And the result of that is what we call the interference pattern on the screen, where you see a series of bright and dark fringes on the screen. So where you see a bright line, that's constructive interference. Where you see a dark spot, that's destructive interference. Now, this is what Thomas Young actually found in his experiment. We do see the interference pattern. We don't see the two bright lines like this. So this is very strong evidence for the wave model of light. Okay, this is something that really only makes sense if we think of light as some type of wave. So here's an animation of the double-slit experiment that Thomas Young did. Again, we have a source of light going through a single slit. Then after that, the light goes through the double slits, and then that gets projected onto the viewing screen where we see the interference pattern. Okay? If you want to see this animation again, here is the link to that. And so after the double-slit experiment became widely known, a lot of people were convinced that light has to be some type of wave. There's just no other way to explain these results unless we think of light as a wave. And for a lot of people, that was just the end of the story. But then in the early 1900s, about 100 years after the double-slit experiment was first performed, Albert Einstein comes along and really throws a wrench in everything. So here we're going to talk about the photoelectric effect. So the photoelectric effect is when light hits a metal surface and then ejects electrons from that metal surface. So this can happen with basically every type of metal. If you shine a light on that metal under the right conditions, you can kick electrons off the metal, and then these outgoing electrons can be measured if you have the right type of devices in your lab. So a lot of experiments were done on the photoelectric effect in the late 1800s, early 1900s, and there were some experimental results that were consistently found. So the first thing to note is that the speed of the ejected electrons depends on the frequency of light, but not the intensity of the light, okay? So it doesn't matter how bright the light is, it just matters that the light has a certain frequency. That's what determines how fast the electrons are going when they get kicked out of the metal. So it's the frequency that matters. Also, electrons are just not ejected at all if the frequency of the light is below a certain minimum value. So if the frequency is high enough, you'll kick electrons out, but if the frequency is too low, then no electrons will be ejected at all. That's sort of the basic picture here. So in 1905, Albert Einstein was able to explain these results by proposing that light consists of particles, which we call photons. And each photon has an energy which is directly proportional to the frequency of the light. So his formula was E is equal to H times F, where F is the frequency of the light, and H is what we call Planck's constant. It's just a constant of nature. So in other words, the photoelectric effect supports the particle model of light, not the wave model of light. In fact, it's really hard to understand the photoelectric effect unless we think of light as being a type of particle. So let's get a little bit deeper into that. So here, let's try to think about what each model of light, the wave model and the particle model, would predict about the photoelectric effect. So again, the idea is we have light coming in, hitting a metal surface, and then ejecting electrons from the metal surface. So how do we expect this to work if light is a wave? Well, if light is a wave, the energy that's absorbed by the electrons in the metal should depend on the intensity of the light. Because, of course, intensity is telling us how much energy is contained in that light wave. And also, the higher the intensity, the more energy the electrons are going to absorb, so the higher the speed of the outgoing electrons. Okay, so that's what we would expect to see under the wave model of light. So now what happens according to the particle model of light? Well, each particle is what we call a photon, and this is typically indicated by gamma on a diagram. We show a little squiggly line alongside that to indicate the photon. The photon hits one of the electrons in the metal, and then it gets absorbed by that electron. Okay, so the particle model predicts that the energy of the photon, which is given by E equals hf, that energy is absorbed by the electron. Okay, so one electron in the metal absorbs one photon, is the idea. So if that energy, hf, is big enough, if it's greater than or equal to some minimum energy, okay, then the electron will be ejected. Okay, and then if not, the electron will remain in the metal. So this minimum energy is what's needed to eject the electron from the metal. So depending on what the metal is, there will be a different value of E min, but there's some minimum energy needed to kick an electron out. And if the photon has that energy, it will kick the electron out. If it has an energy lower than that, then it won't. And again, if the energy of the photon depends on the frequency, just depends on f, then the idea is if the frequency is too low, then we won't be able to kick electrons out. But if the frequency is high enough, then we will be able to. And then if we are ejecting electrons, the higher the frequency, the more energy those outgoing electrons are going to have. In other words, the faster those outgoing electrons are going to move. And that's exactly what happens. The particle theory is predicting all the right things as far as how the photoelectric effect actually works. Okay, it depends on frequency, does not depend on intensity as predicted by the wave model. So again, the photoelectric effect provides really strong evidence for the particle model of light. And so now we find ourselves in a really strange place where we have some experiments that really seem to support the particle model of light, whereas other experiments seem to support the wave model of light, and other experiments can work either way. So this is called, again, the wave-particle duality of light. Now, I'm going to read a quote from Albert Einstein, who really summed this idea up very nicely. So Albert Einstein said that it seems as though we must use sometimes the one theory and sometimes the other. while at times we may use either. We're faced with a new type of difficulty. We have two contradictory pictures of reality. Separately, neither of them fully explains the phenomena of light, but together they do. So in chapters 34 and 35 of the textbook, we cover different phenomena, different things that light does, that can be completely explained using the wave model. Okay? So over the next couple weeks, as we go through these chapters, we'll be focusing entirely on the wave model of light and things that the wave model of light actually gets right. But to go beyond that, to get a more full picture of how light works, you're going to need quantum mechanics. And we're just not going to have enough time in this class to cover quantum mechanics, but I want to tell you a little bit about it. So quantum mechanics is covered in chapters 37 through 39 of the textbook. And in quantum mechanics, everything in the universe, that includes light and that includes matter, everything is described by something called a wave function. And this wave function is a different type of object that we just don't see in classical physics. It has properties of both waves and particles. So to understand the wave-particle duality, we really need quantum mechanics. But again, that's not something we'll be getting to in this class. So as we dive deeper into the wave model of light, we're going to need to be familiar with some concepts and terminology. So in particular, I want to define what's called phase and coherence of waves in this section. So we'll start with phase. What does it mean when we refer to the phase of a wave? Well, the phase of a sine wave is an angle, and that angle tells you what part of the cycle that the wave is on. So to illustrate this idea, let's draw a sine wave. So this is the graph of sine of x plotted against x. So what we're free to do when it comes to phase is pick any point on the wave and just define that to be zero phase. So we're going to arbitrarily pick point A, and we'll say that's the start of the cycle. That's where the phase is equal to zero, okay? So we're going to use the angle phi to refer to the phase. We're going to set that to zero at point A. So then, if we look at point B, which is a quarter of a cycle ahead of point A, then the phase here would be a quarter of a cycle. That would be a quarter of 2 pi, which would be pi over 2. So the phase at point B is pi over 2. Okay, if we look at point C over here, that's 1/2 of a full cycle ahead of point A. So again, if a full cycle is 2 pi radians, then half of that would be pi. So we say the phase at point C is equal to pi. If we go to point D, this is 3/4 of a cycle ahead of point A. So 3/4 of 2 pi is 3 pi over 2. That would be the phase at point D. At point E, we're a full cycle ahead of point A, so the phase there would be 2 pi. Okay? So if we compare points A and E, we're actually back to that same starting point as far as the cycle goes. So what we say is these 2 points are in phase with each other. Okay? At both of these points, we're talking about the same part of the cycle. Okay, if we look at point G, which is back here, since we're behind point A by half a cycle, we're going to use a negative sign for the phase. And again, half of a cycle corresponds to pi. So this would be negative pi is the phase for point G. Now, if we compare that to point C, again, we're talking about the exact same part of the cycle. So we say these are in phase with each other, points C and G. And then finally, if we look at point F, which is over here, that would be a quarter of a cycle behind point A, which means the phase at point F would be minus pi over 2. Okay? And if we look and compare that to point D, again, we're talking about the exact same part of the cycle where the wave reaches a minimum. Points F and D are in phase with each other. That's the idea. So remember, when it comes to a wave, we can express it in terms of displacement d, which is a function of position x and time t. And the general form of this is a times sine kx minus or plus omega t. So in this context, when we're talking about the phase of a wave, we're talking about the argument of the sine function. In other words, the quantity that's inside of the sine function. So this whole quantity, kx minus or plus omega t, is the phase of our wave. So if we know the value of this quantity here, then we know the phase of our wave. Now, remember, if we have two different waves which are combining with each other, it's the phase difference between them, delta phi, that tells us what type of wave we get when we add them together. In other words, this is what determines the amplitude of our resultant wave. So delta phi is defined as phi 2 minus phi 1 for our two waves. And for constructive interference, okay, that's when we get the biggest possible total amplitude. Delta phi can be 0, it can be 2 pi, it can be 4 pi, it can be 6 pi. In general, what we say is it's 2n pi, where n can be 0, 1, 2, 3, and so on. Destructive interference is where we get the smallest total amplitude when two waves combine with each other. In that case, delta phi is pi, 3 pi, 5 pi. So we're talking about odd multiples of pi as opposed to even multiples, which we did up here. In general, we can write this as 2n plus 1 times pi, where n can be 0, 1, 2, 3, and so on. Okay, so these are the constructive and destructive interference conditions for the addition of two waves. Okay, so we'll start by drawing a sine wave like this. And let's label this point on the wave, this first peak, we'll label that point P. Now I'm going to draw an exact copy of that wave down here, where the peaks exactly line up with the first wave. So the same point P lines up with the point P on the second wave like this. And so this would be an example of constructive interference, because the total amplitude of the two waves would just be the sum of the amplitude for wave number 1 and the amplitude for wave number 2. And again, the way we get this to work is if the phase difference is exactly equal to 0. But of course, we could add 2 pi to that, and then we could add 2 pi to that for 4 pi, 6 pi, and so on. These would be the constructive interference conditions, and the idea is the peaks of the two waves line up, and they constructively interfere for that reason. On the other hand, let's say I draw a wave like this, and then I'll draw a second wave down here, but I'm going to sort of invert it. So in other words, where I have a peak over here on the first wave, now I have a minimum on the second wave. So now what's happening is the maximum of one wave is lining up with the minimum of another wave. And so if I think about what the total amplitude is going to be in this case, well, it would be the difference between the two, right? I would actually be subtracting the two amplitudes to get the total in this case. So this is what we would call destructive interference. And how do I get this to work? Well, if this is our point P on the first wave, denoting the first peak on the second wave is not exactly lined up with that. It's over here. So in other words, the second wave is shifted over by some amount compared to the first wave. Well, that delta phi, that phase difference, in this case would be equal to pi, because it's exactly 1/2 cycle shifted over, or pi radians shifted over compared to the first wave. But of course, 3 pi would also work, because if I just shifted over another 2 pi, we're in the exact same situation, or 5 pi, or basically any odd multiple of pi. So this is why the destructive interference condition works. It gets the peak of one wave to line up with the trough of another. And then the constructive interference condition works because the peaks are lining up with each other, ensuring that the amplitude you get is as big as possible. And again, this happens for even multiples of pi. Okay, so I've got a couple questions here for you guys to work out dealing with phase difference between two waves. So in each of these two graphs, I just want you to figure out what is the phase difference between waves A and B. So we have wave A shown in blue, wave B shown in red. What's the phase difference in this first picture? And then what's the phase difference in this second picture? Okay, so pause the video, think about it for a second, try to work it out, and then we'll go through it together. Okay, so let's start with the first graph, the one at the top of the page. What we see here is in comparing waves A and B, they're 1/4 of a cycle out of phase. Okay, so that means delta phi is 1/4 of a cycle, which we can just then convert to radians, where in every one cycle we have 2 pi radians. And so in radians, this would be pi over 2. Okay, so what we'd say about these two waves is that the phase difference is pi over 2. But of course, you can always add 2 pi to that because waves just repeat themselves after 2 pi radians. And in fact, you can add 4 pi, 6 pi, and so on. So what would also work would be 5 pi over 2, 9 pi over 2, 13 pi over 2, and so on. These would also work. Okay? Now for the second example, on the second graph at the bottom of the page, if we compare the two waves, we'll see that they're exactly 1/2 of a cycle out of phase. So the phase difference, delta phi being 1/2 a cycle, if we convert that to radians, where again one cycle corresponds to 2 pi radians, this would be pi. Okay? But again, we can add to that. You can add 2 pi, you can add 4 pi, you can add 6 pi, and the waves will be lined up in the exact same way. So in other words, we have 3 pi, 5 pi, 7 pi, all the odd multiples of pi would also work. Okay? So that's how we sort of quantify the phase difference in these two examples. Okay, so that takes us to the idea of coherence between waves. So we say that two different waves are coherent if the phase difference between them is constant in time. So if you think about it, if we want to have constructive or destructive interference that remains stable over time, we need our waves to be coherent. Because if they're not coherent, let's say in one moment the phase difference between the waves is pi, and in the next moment it's 2 pi, then you're sort of switching between constructive and destructive interference. If you want just stable interference that doesn't change over time, then you need the phase difference to be the same over time. You need the waves to be coherent. Okay? So I'm going to show you an example of coherent and incoherent waves so you can see the difference. So in this first animation, you're going to see this wave shown in sort of dark red color, this wave shown in bright yellow. The sum of the two waves, when we add them together, is shown in blue. Okay? So I just want you to take note of what happens in this case. So first of all, we say the waves are coherent because you can see the phase difference between them is not changing. It's just staying the same over time. And what you get is a blue wave, the sum of the two waves, which has a constant amplitude over time. Okay? So the blue wave, which shows you the sum of the two component waves, stays the same over time. Now, in this next animation, you're going to see these two waves again, and the sum of the two waves is still going to be shown in blue, but this time they're incoherent, meaning the phase difference between them is changing over time. So notice how at first the waves were perfectly in phase, then they went out of phase, and now they're back to being in phase. And so the sum of the waves is going from having a really big amplitude to having zero amplitude when they're out of phase, and then back to a big amplitude once they go back in phase. So we say these waves are incoherent because, again, the phase difference between them is changing over time, and we see that the result of that is the sum of the two waves has a changing amplitude. So that's the difference between coherent waves and incoherent waves. Okay, so an example of a coherent source of light waves would be something like a laser. So we can think of a laser as emitting many different light waves, which are all in phase with each other, and they're perfectly coherent, okay? Something that is incoherent would be something like a light bulb, which is emitting a lot of different waves, and the phase difference between them is completely random. So you're seeing this sort of random mix of phases here. That would be an incoherent source of light. Okay, so that's the difference between coherent and incoherent. So now that we've developed these ideas of phase and coherence, we can really start to get into the details of the double-slit experiment. And in particular, we want to see, how do we describe the interference pattern that's produced in the double-slit experiment? So let's get into that. So remember the basic setup. We have a slit screen where we have a pair of slits separated by some small distance. And then we have a viewing screen, which is where we project the light that goes through the slits. Now, the assumption we're going to make is that the source of our light is coherent. So imagine something like a laser is producing the light that goes through the slits. And so here are the wavefronts of those coherent light waves. Now, the slits are going to be assumed to be very narrow. So each one of the slits, after the light goes through, can be treated as an isotropic source of light waves, meaning we can imagine that the light coming out of the slits is coming from a little point here and here. So here is the wave coming out of the first slit, and here's the wave coming out of the second slit. Now, at the position of the slits, these two waves are in phase, meaning if I have a crest of a wave coming out of this slit, at the exact same time, I have a crest of a wave coming out of this slit. So if we want to understand what we'll see here on the viewing screen, what sort of pattern of light is going to be projected onto the viewing screen, we just have to remember that we're dealing with two separate waves which combine at a certain point on the viewing screen. Now, depending exactly where we are on the viewing screen, we can get constructive interference of those two waves, or we can get destructive interference of the two waves. And the result of that is the interference pattern that we see projected onto the viewing screen. It looks like this. It's basically just a series of bright and dark lines, where we see a bright line, that's where we have constructive interference of the two waves. When we see a dark line, that means we have destructive interference of the two waves, and that's the reason for this interference pattern. So next, we want to get a more mathematical, quantitative description of that interference pattern. In particular, we want to be able to calculate where are we going to see a bright line, where are we going to see a dark line. We want to answer questions like that. So here's the basic setup. We have the slit screen, where we have two very narrow slits. We'll label them 1 and 2. And the distance between those two slits is what I'll call D. Okay, then we have the viewing screen over here. The horizontal distance between the slit screen and the viewing screen is going to be L. So next, we're going to want to be able to locate a certain position on the viewing screen. And there are two different ways we can do that. We can do it with an angle. So this angle theta is measured off of the center line here, which goes right through the center of the two slits. So the angle relative to that line is theta. That's how we can refer to a position on the screen. But we can also do it with a distance y, which is just an actual linear distance off of the center line along the screen. Okay, so those are two different ways we'll sort of locate a position on the screen. Now, the light that's actually hitting the screen, remember, is a superposition or an addition of two waves. One is coming out of slit number 1, the other is coming out of slit number 2. So what we're going to do is write down an equation for each one of those two waves. For the wave coming out of slit number 1, we have this. d1 as a function of x1 in time is equal to a times sine kx1 minus omega t. And then d2 as a function of x2 in time is a times sine kx2 minus omega t. So remember, these two waves are generally going to be traveling different distances to get to the screen, which is why I'm defining a separate x1 and x2 variable to denote the distance each wave is traveling. Okay, so next, we'll think about how to write down the phase difference between these two waves. Now, in general, the phase difference is just given by delta phi equals the absolute value of phi 2 minus phi 1, where each one of these phi values is just the argument of the sine function. In other words, the quantity that's inside of each one of the sine functions for our two waves. So we have kx2 minus omega t for the second wave, and then we have kx1 minus omega t for the first wave, and we're subtracting these two phi values. So the first thing to notice is that the omega t terms cancel out because I have minus omega t here, and then I have plus omega t here. I can also notice that after I do that, I can pull out a common factor of k, and then inside I'll just have x2 minus x1 absolute value, which we can write in shorthand as just delta x. So in other words, the phase difference between the two waves is just given by k times delta x, and that's it. So recall that k is what we refer to as the wave number. K is equal to 2 pi divided by lambda. And delta x is what we call the path length difference between the two waves. The idea here is each wave has to travel a different distance to get to a given point on the screen. Delta x is the difference between those two path lengths. So here is a picture of delta x. We have the first slit. A wave has to travel a distance x1 to get to a certain point on the screen. We have the second slit. A wave has to travel a distance x2 to get to that same point on the screen. So this line represents x1, this line represents x2, and this line in the middle is what we use to measure our angle theta. So remember, we have the center line of the two slits here, and then we draw a line from that to the point on the screen. This angle is what we call theta. So in a real double slit experiment, the distance between the slit screen here and the viewing screen over here, which we refer to as L, is typically going to be a meter or so, somewhere in that ballpark. But the distance between the two slits is going to be absolutely tiny, typically much, much less than a millimeter. So in other words, the distance L is always going to be much, much bigger than this distance D, which means we're showing the diagram kind of with exaggerated proportions. In reality, the horizontal distance L is much bigger than this vertical distance D. And these three lines that we see on the diagram are almost parallel to one another. So because of that, let's take this picture and just draw the two lines for x1 and x2. Again, in reality, those two lines are going to be nearly parallel to one another, so we can show them as making the same angle theta with respect to this horizontal line shown here and here, okay? So we want to find out what delta x is. What is the extra distance that the wave coming out of slit number 2 has to travel compared to the wave coming out of slit number 1? Well, to find that extra distance, we'll start by dropping a perpendicular line down from x1 onto x2 like this. So this distance and this distance starting from where we drop the line down are the same, meaning the extra distance that the wave coming from slit number 2 has to travel is shown right here. This is our delta x, okay? So we'll construct a triangle to really see how to solve for delta x. Remember, this vertical distance is d. This is our angle theta. This is a right angle, as we saw earlier, and this side length in our triangle is delta x. So I'm just sort of copying down the picture and picking out this right triangle that we see from the diagram. And remember, sine theta is equal to the opposite side over the hypotenuse in any right triangle. Here, the opposite side is delta x, and the hypotenuse is d, the distance between the two slits. So if we take that and then solve for delta x, we'll see that delta x is equal to d sine theta, okay? So the path length difference between these two slits is always going to be given by d sine theta. Okay, so if we take what we just learned and apply it to our previous expression for the phase difference, remember delta phi for the two waves coming out of the two slits is given by k times delta x. And we can replace k with 2 pi over lambda, and we can replace delta x with d sine theta as we just worked out. So to simplify that, on top, we have 2 pi times d times sine theta, and on the bottom, we divide out lambda. This is an expression for the phase difference between the two waves coming out of the two different slits. So remember, constructive interference occurs when the phase difference is an even multiple of pi, so 2 pi, 4 pi, 6 pi, or just 0. 0 also works. So what we'll do is we'll set the phase difference delta phi, which is 2 pi d times sine theta over lambda, equal to 2 times m times pi, where m is just a number that can be 0, 1, 2, and so on. That's how we specify that we have an even multiple of pi for our phase difference. So right away we can notice that there's a factor of 2 here that cancels with a factor of 2 over here. There's a factor of pi over here that cancels with a factor of pi over here. And then we can just take this lambda and move it over to this side so it's no longer in the denominator. So the simplified expression becomes d sine theta is equal to m lambda. This tells us exactly where we have points of constructive interference in the interference pattern. This is where the bright spots are located. We can also solve for the destructive interference condition. Remember, destructive interference occurs when the phase difference is an odd multiple of pi. So we have pi, 3 pi, 5 pi, and so on. So again, we'll put delta phi over on this side, 2 pi d sine theta over lambda. And on the other side, we'll just have an odd multiple of pi, which generally we can write as 2m plus 1 times pi, where again, m is just a number, which can be 0, 1, 2, 3, and so on. Just any integer and zeros included. So just like before, cancel out the pi factors, divide out the factor of 2, move the lambda over here, and what we get is d sine theta is equal to m plus a half times lambda. So when we have constructive interference, d sine theta is an integer multiple of the wavelength lambda. When we have destructive interference, d sine theta is half integer multiple of the wavelength lambda. Okay, so those are the two conditions for constructive and destructive interference, and we can use it to locate where the bright spots and the dark spots on the screen are going to be located. Okay, so this is what we would see projected onto the viewing screen in a double-slit experiment. It's a series of alternating bright and dark bands, and we call this entire thing the interference pattern. So a bright band is also known as an interference maximum because it's a point of maximum intensity on the screen. And a dark band is also known as an interference minimum because it's a point of minimum intensity on the screen. So we already have worked out where the interference maxima are going to happen. That's where d sine theta is equal to m times lambda. Now actually, if you take a look at this equation and you plug in m equals 0, then you're going to get out theta equals 0. So in other words, at the very center of the screen where theta is equal to 0, we have a maximum, which is our m equals 0 maximum. Now if we take a look at this equation again, we'll see that the larger the m value is, the larger the theta value will be. So the next bright band is going to be m equals 1. The next one is going to be m equals 2 at an even bigger angle, and then m equals 3, and so on. And by the way, this pattern is completely symmetric. So it's the same going to the right of the center and going to the left of the center as well. So we have our m equals 0 maximum in the very middle, and we have an m equals 1 maximum on either side of that. And then an m equals 2 maximum on either side of that, okay? And everywhere in between, we have the minima. So this is our m equals 0 minimum. We have 1 on either side. This is our m equals 1 minimum, m equals 2 minimum, and that pattern keeps going, corresponding to all of these possible values of m. So the larger m is, the further away from the center we're getting from the interference pattern. That's how that works. So usually in a double-slit experiment, the angles involved are going to be very small, which means we'll typically be able to use small angle approximations to make our equations even simpler. So if you haven't seen the small angle approximation before, I'm just going to run through it real quick and show you where this comes from. And the starting point is a Taylor series. So remember, a Taylor series describes how a function f of x behaves near a given point, which we'll call x equals a. And we can describe how that function behaves near that point using a sum of polynomial terms, okay? And technically the sum is infinite. It goes on forever. So the Taylor series is going to be, we have f of a, so evaluate the function at point a, and then take f prime of a, so evaluate the derivative at point a, and then we'll have x minus a. Then the next term is evaluate the second derivative at point a over 2 factorial, and then x minus a squared. And that pattern just keeps repeating. We'll have the third derivative and then x minus a cubed in the next term, and so on. So it's a polynomial sum. We're not going to work out how to actually compute the Taylor series. We're just going to show the result for sine and cosine near x equals 0. And just to be clear, x is an angle measured in radians, okay? So sine of x is going to be x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7 over 7 factorial. And that pattern keeps repeating. That's how we expand the sine function using a Taylor series. For the cosine function, it looks like this. We have 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial, and so on. That pattern keeps repeating. This is the Taylor series for cosine x, again, near x equals 0. Now, if we assume x is very small, meaning we're dealing with a small angle, meaning x is much, much less than 1, okay, then all of these higher order terms, these higher powers of x, are going to be very, very small. If x is a small number, then x squared is an even smaller number. And x cubed is an even smaller number than that. And then x to the 4th is an even smaller number than that. So because we're dealing with small values of x, all of these higher order terms are negligible. They can basically be ignored because they're so small. So we can actually just keep the first order term, which would be for sine x, that would just be x. For cosine x, that would just be 1. And the rest is so small that we can ignore it. Those are the small angle approximations. We have sine x is approximately equal to x, and cosine x is approximately equal to 1. And this is a good approximation as long as x is much, much less than 1. Okay? So those are the small angle approximations, and that's when we can use them. So to get a little bit of a sense of this, let's do some calculations. What is the percent error in using the small angle approximation for the sine function for an angle of 1 degree? And then as a follow-up, what is the percent error in using the small angle approximation for the sine function for an angle of 30 degrees? So remember, sine theta is approximately equal to theta, as long as theta is much, much less than 1. By the way, we're talking radians here. And the percent error is given by approximate minus exact over exact times 100. So try to make these calculations to see how far off is the small angle approximation in each one of these cases. Pause the video, see if you can get it, and then come back to the video when you think you have your answers.
Okay, so let's work this out. Let's say we have an angle of theta equals 1 degree. So the exact value of sine theta would just be sine of 1 degree. So if you punch that into your calculator, here's what you will get. You'll get 0.017452. Now the approximate value is, again, when we use the small angle approximation, sine theta is approximately equal to theta. Theta has to be measured in radians for this to work. So we'll just have theta measured in radians. So we'll take 1 degree and convert it to radians. So remember, there are 360 degrees for every 2 pi radians. And if you compute that, it's just 2 pi over 360. And this works out to 0.017453. So it's very close. This is a really good approximation. You have to go out to many decimal places before you actually see any difference. So the error is really small. Percent error in this case, which is given by approximate minus exact value over the exact value times 100. So the percent error, if we have an angle of 1 degree, is given by 0.017453 is approximate minus 0.017452 is exact, divided by 0.017452, and then times 100 to make this a percentage. Okay, so if you go ahead and calculate that, you'll get 0.00573%, which is about 0.006%. That is an absolutely tiny error. This is a really good approximation when we have an angle of 1 degree. It's actually, just to give you a sense, this is better than 1 part in 10,000, okay? However, if we go to an angle of 30 degrees, so for theta equals 30 degrees, the approximation is not quite as good. And so, again, the exact value is just sine of theta. So if we take sine of 30 degrees, that's exactly 0.5. The approximate is theta in radians. So we'll take 30 degrees now and convert that to radians. Using the same conversion factor, we have 2 pi radians for every 360 degrees. And this turns out to be 0.524. So it's still pretty close, right? But it's not as close as it was before. So what we're seeing here is that if you increase the angle, of course, the small angle approximation is getting worse. So the percent error in this case is going to be 0.524. That's the approximate value. Minus 0.5, that's exact, over 0.5, that's the exact value again, times 100, which works out to 4.8% or about 5%. So it's still not bad, but it's, again, nowhere near as good as the approximation for an angle of 1 degree. So here, we're only better than about 1 part in 20 with this approximation. So the point is, as the angle gets bigger, the approximation gets worse. Okay?
So as long as we're dealing with small angles, again, that means theta is much, much less than 1 radian, we have a nice approximation for the distance between two adjacent maxima on the screen. So if we have a bright line here and a neighboring bright line here, this distance delta y can be approximated as lambda times L over d. Okay, so that's a nice approximation we have as long as the angles are small. I'll show you how that works out, and then we'll also do an example problem. So here's the example problem. Coherent light of wavelength 525 nanometers goes through a pair of slits which are 0.100 millimeters apart. How far apart are the adjacent bright spots on the viewing screen, which is 1.20 meters away? All right, so let's work all of this out. So we'll start by drawing a diagram of the situation. We have a slit screen. So this is our double slit screen. And the separation between the two slits is D. And then somewhere over here, we have the viewing screen. And the distance between these screens is L. Now, this is the center line. I'm going to show that with the dashed line. It goes right through the center of the slits. And we can locate a point on the viewing screen if we just draw a line from the center of the slits to a point on the viewing screen. And we can locate that point on the viewing screen either with an angle theta, shown here, or a distance y from the center line, shown here. Okay? So we can relate theta and y by remembering that the tangent of theta is equal to the opposite side over the adjacent side on a right triangle. And we do have a right triangle here. The opposite side to the angle theta is y. The adjacent side is L. Okay? Now, if we have small angles, in other words, theta much, much less than 1 radian, we can make some approximations. So remember, tangent, by definition, is sine over cosine. So tangent theta is sine theta over cosine theta. That's not an approximation, that's just an identity. But remember that cosine theta is approximately just equal to 1, assuming small angles. So this is basically sine theta over 1. In other words, tangent theta is approximately equal to sine theta when we have small angles. So we'll keep that in mind. Okay, the next thing we'll do is remember that the interference maxima occur whenever we have d sine theta
equals m times lambda, where m is 0 or any integer, 1, 2, 3, and so on. But using the small angle approximation, we can say sine theta is approximately equal to tangent theta, so d tangent theta is approximately equal to m times lambda. And tangent theta, by the way, as we worked out earlier, is just y over L. So d times y over L equals m times lambda, meaning y is approximately equal to, I should say approximately over here as well, y is approximately equal to m times lambda times L divided by d. These would be the locations of the maxima. Okay? So what we want is delta y, the difference between the locations of two adjacent maxima. So the way I'm going to write this is I have ym plus 1 minus ym. So here, let's take an example. If m is equal to 1, this would be y2 minus y1. If m is equal to 4, this would be y5 minus y4. It's just the distance between two bright spots. So it's the distance between adjacent maxima. Okay, so this would be approximately equal to, given what we just worked out, m plus 1 lambda L over d minus m times lambda L over d. And so if we pull out the lambda L over d, then we'll just have m plus 1 minus m in the brackets, which is just equal to 1. So this proves what we were trying to show, that delta y is approximately equal to lambda L over d as long as we have small angles. Okay, so now to do the calculation for the example problem that we did. So for the example problem, we had a wavelength, lambda, equals 525 nanometers. Let's remember that nano is the same as 10 to the minus 9. So this is 525 times 10 to the minus 9 meters. We also have d, which is equal to 0.100 millimeters. Milli is equal to 10 to the minus 3. So this is 0.100, 10 to the minus 3 meters. Okay? So if we calculate, and then by the way, L, that's the other piece of information here, L is just equal to 1.20 meters. Okay. So delta y, lambda L over d, is just equal to 525 10 to the minus 9 meters times L, 1.20 meters, divided by d, which is 0.100, 10 to the minus 3 meters. So unit-wise, this comes out in meters. And if you calculate the result, you'll get 0.00630 meters, which is the same as 6.30 millimeters. So in this example, the bright spots are separated by 6.30 millimeters on the screen. Okay?
And so I think we'll end this video here. We'll wrap up chapter 34 in the next one. So until then, as always, be safe, be healthy out there. Take care.